All right, Chapter 10. Chapter 10 is all about three-dimensional objects. So we're moving away from 2 dimensions and going into 3 dimensions, which can be a little bit challenging to draw, but there's a lot more real-life problems that involve 3 dimensions, so that part's kind of cool. Today's going to be a little bit of an overview of all the shapes, all the solids, but then we're actually going to mainly focus on finding surface area of just prisms and cylinders. So a little bit of intro, and then we have 4 examples to kind of jump into. Alright, so right here in the very beginning, it says three-dimensional figures or solids can have flat or curved surfaces. Prisms and pyramids are named by the shape of their bases. So the base, we normally think about the base kind of as this bottom section here that's on the ground. But it depends. Sometimes it's turned on its side and the base might not be on the ground. But traditionally, that's kind of where it's at. So if you look at like down here, this one is named a triangular prism. Triangular because the shaded areas, the bases are triangles. This one is rectangular prism, or a box. Rectangular prism is just a fancy name for a box, because it has bases. Now, realize that this rectangular prism could be laid on its side. You know, this prism right here could be laid down long ways, like this. And then if I kind of come up here and redraw it like this. And now the base could be here. So rectangular prism, you got a couple options. Your base could be the long one, or your base could be kind of the smaller side, the little square, the little rectangle here. But the key is the bases have to be parallel. So bases must be parallel if you are a prism. So for prisms, the bases must be parallel. So notice on the triangular prism, these two triangles here, those are parallel to each other. They're flat surfaces on the top and bottom. If I were to try to lay that thing over on its side, I would not have, because there's only 3 sides, I wouldn't have another base that's parallel to him. So that's really not going to work out. So it has to kind of sit that way for the bases. Now in the next few sections we're going to get into pyramids. Pyramids only have one base, so you'll notice you have the triangle down here at the bottom, but then there's no matching triangle. They actually just come all the way up there to a point. And you can have triangle bases, rectangle bases, you can have hexagon pyramids. So the first name here represents the base or the bottom. The second name says how many bases do you have. Do you have 1 or 2? Now, cylinders are kind of similar to prisms in that cylinders also share parallel bases. All right, but instead of now it being a polygon on the bottom, like a triangle or a rectangle, you now have circles, or down here at the bottom. They look like an oval, but cylinders are really circles. If you think about like a Mountain Dew can or any type of soup can or object like that. And then a cone is kind of similar to a pyramid where you only have the one base on the bottom and then they come to a point or a vertex on the top. Now some other vocabulary that we might kind of get into as we're going through this. Let me bring that back. So an edge, these lines right here, these are referred to as edges, these sharp kind of creases where the two planes come together. All of these blue lines I'm drawing here are called edges. Okay, kind of picture a room. It would kind of be like the seam where the walls meet in the room. All right, so if I ask you to count the number of edges, this shape here has 4 on the top, 4 on the bottom, and 4 walls. So this shape I drew over here, actually, or I didn't draw it, computer did. I have 12 edges. Now the vertex is where the faces meet each other. So I have these corners here. So each one of these corners, these are called the vertices. So I have 8 vertices, which is just plural for one vertex. And then the flat surface, the sides are called the face. So these can be called sides, or sometimes I refer to them as walls because it's kind of easier to think of the walls. So when I look at the faces, this thing has 6 faces. You know, because you basically have a top, bottom, front, back, left, right. So 6 faces for this one would be top, bottom, the front, and the back and the left and the right. This is probably the most important piece of all of them, because when you find surface area, you're basically finding the area of all the faces and then adding them together. The edges and the vertices, they're nice to kind of talk about, but they're really not going to be used to calculate anything. It's going to be the faces where the importance is. All right, well, let's kind of zip down and let's get into some problems and see what we're dealing with here. So you have another vocab term called a net, and basically a net is just a diagram of a 3D figure. It's kind of when you unfold it. So if you start with this rectangular pyramid over here, it has a rectangle base on the bottom, and then you were to open it up, this right here will be referred to as the net. And so to find the total surface area, all you would do is you would add up, you'd add up A plus B plus C plus D plus E, and when you add up all those areas, that would end up giving you the total surface area. So that's kind of to visualize. That's kind of a skill that we kind of need to have, is picture what something's going to look like when it unfolds or when it folds. So over here down below, there's a couple more examples, and I'll go into this cylinder one in a little bit more detail. So another kind of term that I don't see on here, but I want to throw out. Normally, the top and the bottom here, these two in blue, we'll call these are the bases. And these sides here, this one and this one, and then the front and the back, those are called lateral faces. The lateral faces are kind of what I call the walls, the up and down, the vertical portions. The bases are the horizontal pieces. Now on a cylinder, so when you look at a cylinder over here to the far side, this right down here, this would be referred to as the lateral area, okay, the walls. Because on a cylinder, your base is going to be this top portion, and then they don't really have it drawn here, but if I kind of extend it out, in blue, these are the bases. So those are the bases, and the walls kind of wrapping around would be called the lateral area. Now, a lot of times over here on this side, everything is pretty much a square or a rectangle. Over here on the other side, when you open this thing up, you're basically going to have the lateral area, but then when you unfold it, you're going to have a top and a bottom. So this is your net for a cylinder. And when you're kind of trying to figure out the area, the surface area, well, the circles are pretty easy. We did this last chapter. This is pi r squared, and this is pi r squared. So I basically have two circles, all right? I have two pi r squareds. That knocks out both circles. But then when you're trying to find the area of this rectangle, well, the area of a rectangle is just base times height. And the height, is right there, which is the height of the cylinder. However, the base is a little bit tricky, because the base, or the length of this rectangle, is basically going to have to match the distance all the way around the circle, because when you fold it up, or when you unfold it, which is kind of shown right here, it has to match the circumference. So the circumference, we know from last chapter, is 2 pi r. So my base is basically 2 pi r. So now when I do that rectangle, when I do the area of the rectangle, it's going to be the base times the height. So this is basically the two circles, and this is the rectangular, the lateral area for the cylinder. So if you just want to use this formula, this will knock out the surface area for a cylinder. All right, let's do some examples with some numbers and see if we can kind of break this down a little bit. So example 1 says sketch a net for the rectangular prism. We may not sketch a net for every single one. Sometimes it's just easier to write them out. But I will for the first one here, maybe the first couple. Nets are just kind of useful if you're struggling and you need to figure out what the surface area represents, but you might be able to just list out all the faces and do it that way as well. So to do this net, I'm going to start with the bottom rectangle. So I'm going to kind of take this rectangle down here, this base that it's sitting on, and I'm going to draw that one. All right. And it doesn't really matter what direction you kind of draw it in. I'm going to draw it right here. And this thing is 6 feet by 10 feet long. All right. So that's the bottom rectangle. And I'm going to come back and erase this so I can see it easier. Now, if I let all the walls fall down, okay, if I let all the walls just kind of drop, on the ends, I have this wall right here. I'm going to draw right down here at the bottom. And that wall has a length of 7. It's 6 by 7. And then if I do this back wall over here, if I let this wall fall down, this wall is 10 by 7. And then if I let this wall fall down, that's going to go up here. And that's also has a height of 7. And it's still 6 because it's connected to the base. I'm going to actually change these two to make it a little bit easier to see. I'm going to write those numbers inside. So these blue numbers are the base, the rectangle on the very bottom, and everybody else is the walls. So this has to match up 10, this has to match up 6, this has to match up 6. And then when I draw this face or this wall right here on the front side, I'm going to let this one fall down. And this is 10 by 7, 10 by 7 all the way around. And then I can't forget about the top. So this top piece up here, this piece can actually fall from any of them. All right, it can be hooked to anybody. I'm going to just kind of put the top, I don't know, maybe over here. And this better match your other kind of original base there. And this guy is 10 by 6. All right, so there's my net. I've done part A, and now I'm going to go through and find the area of each face. So let's just kind of go through. I'm going to write these in purple. The area of each face. Well, the top and the bottom, those are both 60. 6 times 10 is 60. The walls, well, the ends here, this wall here on the end is 42. It's 6 times 7. And the other end on this side is 42. And then the last pieces over here are 7 by 10. These are 70. All right. So basically my box should have some matching pieces. My top and my bottom are both 60 plus 60. If I call this piece here the front, my front and my back are both 10 by 7. So those were 70 plus 70. And then my right and left, call this one the left and this one the right. My right and left were both 42 plus 42. So if you notice, I have six different faces or 6 areas. And all sides are accounted for. So I put all those numbers together and I get basically 120, 140, and 82. Put all those together for a grand total of 342. And my units here are going to be feet squared, square feet, because we're doing area. Since I'm doing area, I have to square the units there. So I sketched the net, I unfolded it, and that's what I come up with. Now, you can get the answers a lot quicker than this without doing the net and just kind of doing them separate. So I'm going to do this one a little different. For number 2, I'm going to not sketch the net, and I'm basically just going to handle these individually. So when I do the top and the bottom, they should match each other. They should always match each other on a prism. So basically I have 2 triangles. All right. So 2 triangles is basically 2 times, and a triangle is 1/2 base times height. So that's what 2 triangles are. So when I look at this triangle, has a base of 4 and has a height of 3, because if I look up above here, I see the 3 up top, so that matches the 3 on the bottom. And this might be helpful. Maybe I'll color code this a little bit. Some people struggle with triangular prisms. Maybe I'll color code this and just kind of show you that this 2 would be this height, and this height. Those are all 2s. They're all a height of 2. The 4 is this length and this length. Those are the 4s. The 5 would be these 2 lengths. That's 5. And then the 3, that would be those 2 lengths. So that might help you when you're kind of trying to visualize and put all this together. So 2 1/2 base times height, so that would be 2 times 1/2. And now my base is going to be right here. My base is 4 for the triangle. And my height of the triangle is the green line. The green line is right here. Base and height, remember, meet at 90 degrees. So that would be 3. So just for my top and my bottom, I'm at 2 times 1/2 is 1 times 4 times 3. That's at 12. So I have 12 for my top and bottom. And now my walls, I still have to add the walls in there. Well, there's 3 different size rectangles. There is, I'm just going to kind of list them like this. You have this front rectangle right here that's 4 by 2 or 8. You have this back rectangle over here that's 3 by 2 or 6. And then you have this one over here, this far side, that's actually 5 by 2, which is 10. So 8 plus 6 plus 10 for a grand total of 24. So now I do my 12 plus my 24. So 36 meters squared would be the total surface area. I just put SA for surface area. Now, something I want to kind of point out, because there are other formulas floating around out there. I always just find all the individual faces and add them up. But there are some other formulas some people use. Basically, when you're finding the top and the bottom, this is your base area. And the walls are what's called your lateral area. So just if you're looking at vocabulary, base areas versus lateral areas, that's kind of how some people break them down differently. And I think tomorrow I will give you kind of a shortcut formula if you'd like to use it for prisms that you can use. It makes things a little bit faster, but I'm going to hold off for right now. All right, moving on down. A couple more examples. Same type of prism, but now instead of a triangle or a rectangle, we have the Pentagon prism. So just first thing I'm going to do is I'm going to name this thing. This is a pentagonal prism. It's a prism because the top and the bottom base are parallel to each other and they're congruent. And it's a pentagon because it has 5 sides. So let's knock out the bases. So let's do the base areas. And then we're going to add to that the lateral area, which would be all the walls. So this is the walls, and this is the top slash bottom. All right, so the base area, the pentagon on the bottom. Well, that base area we know is 1/2 apothem times perimeter. Okay, that's the base areas. And I have 2 of them. I don't just have one, I have 2 of them. I have a top and a bottom. So I got to kind of do 2 times in the front. My lateral areas are all rectangles. And the nice thing about this type of prism is I have congruent rectangles all the way around that thing. So that's going to be kind of nice. So basically, my lateral areas, rectangles are base times height. And I know that I have 1, 2, 3, 4, 5 of those rectangles. All right, 5 base times height. So let's do this. Let's put our numbers in here. So I have 2 times 1/2, which that just comes out to be 1. The apothem for this shape is 4.8. Remember, the apothem is right here. It's a dotted line. The perimeter of the shape, well, it looks like each piece is 7. So when I do 7 all the way around, 7 times 5, so the perimeter would be 7 times 5, or 35. So now I can get the area of the two bases, and I'm going to add to that. Now each rectangle separately is base times height, but I have 5 of them. So I have 5 rectangles that are all base times height. Well, each rectangle, when I break it down, has a base of 7, okay, because these are all 7 all the way around. Base of 7, and then my height is over here on the side. My height is 12. All of these blue lines right here are 12s. All the red lines are 7s. So when you basically look at every single rectangle, it's 7 by 12. So 7 by 12. And now we're just going to have to jam all this stuff into the calculator and get the answer. So here on the left-hand side, I have 2 times 1/2, which that's just 1. I don't even need to punch that in. So basically 4.8 times 35 equals, so that's 168, plus 5 times 7 times 12, which is 420. And you combine those two together, and you get 588. Since it's area, it's going to be square yards. So this is the total. Now again, if they wanted just base area, or if they wanted lateral area, you know, sometimes problems just want the base areas or the lateral areas. You could break them down individually. I strongly suggest you keep everything separate, because you'll get partial credit on problems where, you know, they're short response, or you actually come up with your own answer. All right, last one, cylinder. So sketch a net. I'm actually going to do a net on this one. I think it's kind of helpful. So I'm basically going to have my base, or my lateral area, which I call that LA sometimes. So there's my lateral area, the walls, and my circles are going to be my 2 base areas. Okay, 2 base areas are circles, lateral area is the rectangle. So we know that these base areas, this should be pi r squared, and this should be pi r squared. And we need to know the radius. Well, the radius, r, is 2. So pi times 2 squared, this would be 4 pi. This dude right here is going to be 4 pi. And now I'm going to move into my lateral area. So my lateral area is a rectangle with a height of 5. So that's the height. That one's pretty easy. And now comes the tricky part. Now I'm going to bust out the length of this rectangle, which I know the length of this rectangle has to match the length around the circle, which we call circumference. So you're going to need to figure out circumference. The circumference is 2 pi r, or 2 pi times 2. So that's also 4 pi. So that's kind of nice. So now the area of this rectangle here is base times height, which is 20 pi. So now you can pretty much slap all these guys together. So I have my 2 circles. I have 4 pi plus 4 pi, and then I'm going to add 20 pi. Notice I'm not touching my calculator as far as pi or decimals go to the very end. So I have 8 pi for the base areas, 20 pi for the lateral area, so a grand total of 28 pi, and this is meters squared. Now, if you want, you can leave it like this, but some problems are going to want us to turn that into a decimal, so I'm actually going to crank that out really quick. 28 times pi, boom, about 87.96. 87.96 meters squared. Now, you might say, well, where in the heck are we ever going to need this stuff? Why do I ever, care about that? Any type of packaging engineer or a person that designs, a cylinder cans are very, very common. You look in the grocery store, I mean, all types of different beans and soups and broths and juice cans. A lot of cans are cylinders. Well, basically what surface area is just finding how much metal, how much, whatever it is, aluminum or stainless steel or metal, but how much metal would be needed to make this can. All right. So, and the answer would be, this would be a big one, 5 meters tall. That's like over 15 feet tall. So this is almost like a silo for a farm. Some silos are in this type of shape. But this would tell you how much sheet metal you'd need to build one of those. All right, I think you got enough to get started on the practice. The notes were a little long today, but there were a lot of formulas to kind of flush out. So I will see you tomorrow. See you.